Hello friends, welcome to this video session of Refrigeration and Air Conditioning unit number 3. In today's lecture, we will cover multi-compressor, multi-evaporator and cascade system of vapor compression refrigeration system. My name is Mr. S.V. Kumbar, Assistant Professor, Sharad Institute of Technology, College of Engineering, Yadra, Ichalkaranji. So first, we will start with introduction. In previous unit, we have studied a single stage vapor compression refrigeration system, but a single stage vapor compression refrigeration system has one low side pressure, that is evaporator pressure, and one high side pressure, that is condenser pressure. These systems are adequate as long as the temperature difference between evaporator and condenser is very small, that is temperature lift is very small. The temperature lift can be large either due to the requirement of very low evaporative temperature or due to the requirement of very high condensing temperature. In frozen food industries, the required evaporator can be as low as minus 40 degrees centigrade, while in chemical industries, the temperature as low as minus 150 degrees centigrade may be required for the liquefaction of gas. So in that case, single stage vapor refrigeration system will not work at all. So before going to start multi-compressor system, let us learn about effect of decreasing evaporative temperature on TS and pH diagram. So here pH and TS diagram is shown for different evaporator temperature. Now we will start with first. Let us consider 1, 2, 3, 4. 1 to 2 represent it's a compression from vapor to superheated condition of refrigerant. Compression takes place. Now after that 2 to 3 condensation at constant pressure. Here at 3 refrigerant is converted to liquid, that is high pressure low temperature liquid refrigerant. This high pressure low temperature liquid refrigerant, it then flows to expansion valve where its pressure drops down, and again it is sent back to evaporator where here it absorbs latent heat from an object which is to be cooled and it is converted into vapor, and the cycle continues. If you consider another cycle 1 dash, 2 dash, 3, 4 dash. Similarly 1 double dash, 2 double dash, 3, 4 double dash. So what does it mean? Here evaporator temperature decreases from 1 to 1 dash, 1 dash to 1 dash, 1 double dash. As evaporative temperature decreases, there are throttling loss that will increase. Superheat loss will also increase, because if you consider this pH diagram, superheat loss means as evaporative temperature goes on decreasing with single stage vapor compression refrigeration system, superheat loss will also increase. Compressor discharge temperature also increases. Here if you observe TS diagram for 1, 2, 3 and 4, the temperature would be T2. But if the evaporative temperature decreases, here temperature T2 is shifted to T2 dash. Again, if evaporator temperature is further decreased to 1 dash, 1 double dash, here its compressor pressure is also decreased to T2 double dash. So compressor discharge temperature increases as evaporative temperature decreases. Next one, quality of vapor at the inlet of evaporator also increases. Specific volume at the inlet of compressor increases. As a result of this, the refrigeration effect decreases and work of compression increases. That's why we can't use a single stage vapor compression refrigeration system for very low temperature refrigeration. The volumetric refrigeration effect also decreases rapidly as the specific volume increases with decreasing evaporative temperature. Similarly, the effect will get through in the same proportion when the condenser temperature increases for a given evaporative temperature, and due to this drawback a single stage refrigeration system are not recommended when the evaporative temperature becomes very low or when condenser temperature becomes very high. So in such cases, multi-stage systems are used in practice generally for fluorocarbon and ammonia-based refrigeration system. A single-stage system is used to an evaporative temperature of minus 30 degrees centigrade only, and a two-stage system is used up to minus 60 degrees centigrade, and a three-stage system is used below temperature minus 60 degrees centigrade. Apart from high temperature lift application, multi-stage systems are used in application requiring refrigerant at different temperature. We will take one example here. In a dairy plant refrigeration, it may require minus 30 degrees centigrade for making an ice cream and at 20 degree for chilling milk. In such cases, it may be advantageous to use multi-evaporator system, one evaporator which is used for making an ice and one evaporator which is used for chilling milk. So in such application it will be very advantageous. A multi-stage system is a refrigeration system with two or more low side pressures. Multi-stage systems can be classified into multi-compression system, multi-evaporative system and cascade system. So in the next part here up, we will start with multi-compression system. Before that, flash gas removal using flash tank. Generally, problems with high temperature lift application is the high quality of vapor, that is flash gas, at the inlet of evaporator. Flash gas does not contribute to refrigeration effect as it is already in vapor form. It will not extract heat energy from an object which is to be cooled, and it increases pressure drop in the evaporator. So it is possible to improve COP of the refrigeration system if the flash gas is removed as soon as it is formed and recompressed to condenser pressure. However, continuous removal of flash gas as soon as it is formed and recompressing it immediately, it is difficult in practice. So one of the way of improving performance of vapor compression refrigeration system is to remove flash gas at an intermediate pressure using a flash tank. So we will start with flash gas removal using flash tank. Now in this figure a flash tank is shown, and there are three total different ways. So first, to the compressor, second through expansion valve to evaporator, and from the condenser. So 3, 6, 7, 8, 9. So in a flash tank the refrigerant liquid and vapor are separated at an intermediate pressure Pi using a low side float valve, that is process 6 to 7. Here it is shown. The float valve also maintain a constant liquid level in the flash tank. And this is the pH diagram for flash gas removal. The saturated liquid at a point 8 is fed to evaporator after throttling it to the required evaporative pressure, that is PE, that is point number 9, using expansion valve. The saturated vapor in the flash tank is either compressed to condenser pressure or throttle to evaporator pressure directly. Intercooling in multi-stage compression. So generally, why do we require intercooling? If we use intercooling, the work required to run an compressor decreases, right? So this is the pH diagram. Instead of compressing vapor in single stage from state 1 to state 2 dash, like this, from state 1 to directly state 2 dash. If the refrigerant is compressed from state 1 to intermediate pressure 2 like this, intercooled from 2 to 3, and then compressed to the required pressure, reduction in work input result means instead of compressing 1 to 2 dash directly, first compress vapors of compression in first compressor 1 to 2, then intercooling is used from 2 to 3 constant pressure intercooling, and after 3 to 4 again if you compress in a second compressor, the work which is required will be less as compared to if you directly compress vapor from 1 to 2 dash. So this much of work can be saved. So intercooling not only reduces the work input but also reduces the compressor discharge temperature, leading to better lubrication and longer compressor life. That's why generally in most of the dairy or most of the chilling plants we go for multi-stage compression. Intercooling using external water cooled heat exchanger. So as I told you, if you compress refrigerant in more than one compressor, it is known as multi-stage compression. So here first a low stage compressor is shown. So refrigerant from evaporator is compressed in low stage compressor. Here pressure is increased, pressure as well as temperature of refrigerant is increased. This high pressure high temperature vapors of refrigerant is then passed through water cooled heat exchanger, that is intercooler. So here constant pressure temperature drop down takes place. So this pressurized, that is high pressure low temperature vapors of refrigerant, again it is compressed in the high stage compressor, and after again compression in high stage compressor, this high pressure high temperature vapors of refrigerant is sent to expansion valve, then to evaporator, and after through evaporator again it is sent back to low stage compressor. So depend upon availability of sufficiently cold water to which the refrigerant from low stage compressor can reject heat. The refrigerant at the inlet to high stage compressor may not be saturated in this case. Intercooling using liquid refrigerant in a flash tank. So in earlier figure we had used flash tank. Now in this case, first refrigerants are compressed in the low stage compressor, then it is sent to flash tank where it is converted into again high pressure high temperature in high stage compressor after passing through flash tank, and this high pressure high temperature vapors of refrigerant it is sent to evaporator, and after that again it is sent to. So intercooling using in the flash tank may or may not reduce the power input to the system as it depends upon the nature of refrigerant. The heat rejected by the refrigerant during intercooling generates additional vapor in the flash tank, which has to be compressed by the high stage compressor. Thus, the mass flow rate of refrigerant through the high stage compressor will be more than that of low stage compressor. So whether total power input to the system decreases or not depends on whether the increased power consumption due to higher mass flow rate is compensated by reduction in specific work of compression or not. For ammonia, the power input usually decreases, but however, the refrigerant such as R12, R22, the power input marginally increases. So one of the design issues in multi-stage compression is the selection of suitable intermediate pressure. For air compressor with intercooling to the initial temperature, the theoretical work input to the system will be minimum when the pressure ratios are equal for all stages. Therefore, a two-stage air compressor with intercooling is used, and intermediate pressure Pi is equal to P low square root of P low into P high. That is, high pressure will be there on compressor side and low pressure will be there on evaporator side. For refrigerant correction factor to the above equation are suggested. For example, in one such relation, Here Pi is equal to square root of Pe into Pc into Tc upon Te, where Pe and Pc are the evaporator and condenser pressure respectively. Tc and Te are condenser and evaporator pressure temperature in degree Kelvin. Multi-stage compression system with flash gas removal and intercooling. So in earlier two part we have studied multi-stage with flash gas removal and multi-stage with intercooling. Now in this case both systems are implemented, means here it's a first compressor. In first compressor vapors of refrigerants are compressed and it is sent to intercooler. Here it is that in intercooler its temperature drops down but pressure will remain as it is. It is sent to flash chamber, and after flash chamber this high pressure vapors of refrigerant is again compressed to second compressor. Again it is compressed and high pressure high temperature vapors are sent to condenser. In condenser there is a rejection of heat, and after this it is sent back to evaporator through throttle wall and flash chamber. In evaporator, latent heat energy is absorbed from the object which is to be cooled, and again low pressure vapors of refrigerant is sent to compressor. And this is pH diagram for multi-stage system with flash gas removal and intercooling. So it is assumed that in this superheated vapor it gets the refrigerant completely desuperheated and emerges out as saturated vapor at state 4. Now COP of the system, coefficient of performance of the system, can be calculated as COP is equal to QE upon W1 plus W2. QE is the refrigerating effect and the work which is supplied to both the compressor, that is W1 plus W2, which is equal to M1 into H1 minus H9 divided by M1 into H2 minus H1 plus M2 into H5 minus H4, where M1 is the mass flow rate of refrigerant through compressor 1 and M2 is the mass flow rate of refrigerant through compressor 2. Advantages. So first advantage is quality of refrigerant entering the evaporator reduces, thus giving rise to higher refrigerating effect, lower pressure drop and better heat transfer in evaporator. Second advantage of this system is throttling losses are reduced as vapor generated during throttling from PC to PI is separated in the flash tank and recompressed by compressor 2. Volumetric efficiency of compressor will be high due to reduced pressure ratios. Next advantage, compressor discharge temperature is reduced considerably. But however, there is one big disadvantage is that since refrigerant liquid in the flash tank is saturated, there is a possibility of liquid flashing ahead of the expansion valve due to pressure drop or heat transfer in the pipeline connecting the flash tank to the expansion device. Now we will start with multi-evaporator system. In multi-evaporator system, there are many applications where refrigeration is required at different temperature. In earlier part, we have studied if a dairy wants to store ice cream at minus 20 degrees centigrade and chilling milk at 20 degrees centigrade. So in that case, we can go for multi-evaporator system. Or one more example here is in typical food processing plant, cold air may be required at minus 30 degrees centigrade for freezing and 7 degrees centigrade for cooling of food products or space cooling. So in that case also we can go for multi-evaporator system. One simple alternative is to use different refrigeration system to cater the different loads. But however, this may be economically viable due to high total initial cost. And another alternative is to a single refrigeration system with one compressor and two or more evaporators. So multi-evaporator system is classified into two. First, evaporator at the same temperature. In that case, single compressor is used. And second, evaporator at the different temperature with individual expansion valve. In that again, there are three classification: single compressor, individual compressor, and compound compression. We will start with evaporator at same temperature. So here in this figure, one compressor is shown. One compressor is shown. This compressor will compress vapors of refrigerant to high pressure, high temperature. This high pressure, high temperature vapors of refrigerant flows through condenser, and through this condenser, when it passes here, latent heat energy is rejected to cooling medium. Because of this, it is converted into high pressure, low temperature liquid refrigerant. This high pressure, low temperature liquid refrigerant, when it passes through expansion valve. Now if you observe carefully, only one expansion valve is used. Means here there are three evaporators, but the temperature will remain same. That's why only one expansion valve is used. After this, it is converted to low pressure, low temperature liquid of refrigerant. And when it passes through separate evaporator, evaporator 1, 2 and 3, the temperature remains same in all the evaporator, and this is pH diagram for given case. Next, evaporator at different temperature provided with individual expansion valve. Now in earlier case only one expansion valve was provided, but in this case there is a separate expansion valve for each and every evaporator. Therefore, different temperature can be achieved in these three evaporator with a single compressor and single condenser. This is the pH diagram for given case. Here evaporative 1 will be having lowest temperature, after that evaporative 3, 2 and 3 respectively. Next one, evaporators at different temperature. Individual expansion valve is used. Now in this case, individual compressor is used for separate evaporator, as well as separate expansion valves are used, but a single condenser is used for this system. So consider first compressor 1. Here vapors of refrigerants are compressed, due to which high pressure, high temperature vapors of refrigerant flows through condenser, and after that it flows through expansion valve, and then it flows through evaporator 1. Similarly, in case of compressor C2 and compressor C3, here again we can get different temperature in evaporator. Next one, evaporators at different temperature with individual expansion valve. So in this case also, compressor 1 is connected to compressor 2, which is connected to compressor 3. Here we call it as compound compression. And after that, this high pressure, high temperature vapors, again it is converted into high pressure, low temperature liquid refrigerant, and it is splitted to evaporative 1, evaporative 2, evaporator 3 through expansion valve 1, E1, E2, E3 respectively. Next, evaporator at different temperature, multiple expansion valve. So here multiple evaporator at different temperature with compound refrigeration and multiple expansion valve and flash intercooler is used in between these refrigeration system. So first it is first refrigeration system, after that it is sent to flash intercooler, then second refrigeration system works, then this refrigerant is sent to flash intercooler second, and this system works. So in this way multiple evaporator at a different temperature works. A limitation of multi-stage refrigeration system. There, since only one refrigerant is used throughout the system, the refrigerant which is used must have high critical temperature and low freezing point. Second limitation is that the operating pressure with a single refrigerant may become too high or too low. Generally, only R12, R22 and ammonia system have been used in multi-stage refrigeration system, as other systems, that is other working fluids, may operate in vacuum at or very low evaporator temperature, and there is a possibility of migration of lubricating oil from one compressor to other compressor, leading to compressor breakdown. These limitations can be overcome by cascade refrigeration system. Now, what is cascade refrigeration system? So in a cascade refrigeration system, a series of refrigerant with progressively low boiling points are used in a series of single stage unit. The condenser of lower stage system is coupled to the evaporator of next higher stage system, and so on. The component where heat of condensation of lower stage refrigerant is supplied for vaporization of next level refrigerant is called as cascade system. So this is cascade system. So what is done here? There are two sides: high temperature cascade compressor and low temperature cascade compressor. So first, in low temperature cascade refrigeration, when this high pressure high temperature vapors of refrigerant, when it is compressed, it is sent to condenser. Here it is known as cascade condenser. Here heat exchange takes place between these two refrigerant, and here after this high pressure low temperature liquid refrigerant flows through expansion valve, and after that evaporator, right? And at the same time, at high temperature cascade compressor, when it flows through condenser, after evaporation, expansion valve, and after evaporator. So condenser of first, that is low temperature cascade compressor, is nothing but evaporator of high temperature cascade compressor. This is nothing but cascade. Condenser of first refrigeration system is the evaporator of second refrigeration system. So this system employs two different refrigerant operating in individual cycle. They are thermally coupled in the cascade condenser. The refrigerant selected should have suitable pressure temperature characteristic. We will take one example here. Carbon dioxide. Carbon dioxide, its normal boiling point is minus 78.4 degrees centigrade, and its critical temperature is 31.06 degrees centigrade in low temperature cascade. And ammonia, its normal boiling point is minus 33.33 degrees centigrade, and its critical temperature is 132.25 degrees centigrade in high temperature cascade. So it is possible to use more than two cascade system, and it is possible to combine multi-stage system with cascade system. Applications of cascade system. So first application is liquefaction of petroleum vapors. Second, liquefaction of industrial gases. Third, manufacturing of dry ice, that is solid carbon. Fourth, deep freezing. Advantages of system. Since each cascade use a different refrigerant, it is possible to select a refrigerant that is best suited for the particular temperature range, that is very high or very low pressure can be avoided. Second, migration of lubricating oil from one compressor to other is prevented. Cascade refrigeration system. Let M1 is the mass of refrigerant flowing through low temperature cascade system. M2 is the mass flow rate of refrigerant flowing through high temperature cascade system, and M1 is equal to 210 Q upon H1 minus H4 kg per minute. The mass of refrigerant M2 required in high temperature cascade in order to liquefy the refrigerant of low temperature cascade in the cascade condenser is obtained by balance of both system, that is heat absorbed in high temperature cascade system is equal to heat rejected in low temperature cascade system, which we can equate here M2 into H5 minus H8, which is equal to M1 into H2 minus H5, which is equal to M2 is equal to M1 into bracket H2 minus H3 divided by H5 minus H8, which is equal to M1 into H2 minus H4 divided by H5 minus H8. Here H3 is equal to H4. COP of two-stage cascade system. So work done by low temperature cascade system is given as W1 is equal to M1 H2 minus H1 kilojoule per minute, and work done by HT cascade system is given as W is equal to M2 H6 minus H5. So the cascade system power required is given as W is equal to W1 plus W2, that is M1 H2 minus H1 plus M2 H6 minus H5 kilojoule per minute. So power P is equal to W upon 60. So divide this equation entirely by 60, we will get power required to run cascade system. Refrigerating effect is given as 210 Q kilojoule per minute, and COP is given by refrigerating effect upon work done. So refrigerating effect is 210 Q upon work done is this one, M1 H2 minus H1 plus M2 H6 minus H5. So for this video lecture we will conclude. Thank you very much.